All right, now that we've graphed some of our exponential functions, we're going to actually look at the inverse of an exponential function, which we call a logarithmic function. Now, you've probably seen logs at some point in your mathematical career, but logs are just kind of a fancier way to write our exponents. So in general, if you have some exponential relation, let's say we have this exponential relation y equals b to the x. So obviously this is taking some value, some base, raising it to an exponent to get some value, okay? So here's a base, and here's our exponent. And so here's our value over here. So a lot of times that's fine, and we could take b to the exponent, but when you don't know the exponent, that could be somewhat tricky. So if you know the value of b and you know the value of x, you just take b to the x. But what if you know the value of y and the base, but you don't know the exponent? Well, in these cases, it's sometimes easier to use a logarithmic equation. So logarithmic has the same things as an exponential equation. A value, a base, and an exponent is just in a different order. The exponent is all by itself. We add this word log, but there's the base, and there's the value. So it's just getting it rearranged. So in an exponential form, if you have the base and exponent, that's great. But if you have the exponent or the base and the value and you want the exponent, a lot of times it's better to change to this log form. So rearranging the value, base, and exponent, and then adding, of course, the word log, which is representing that. So in general, very important, a log is simply what exponent gets raised to the base to get the value y. So we're just trying to find exponents. So anytime you see the word log, it typically is talking about exponents, some exponent I need. So your calculator is very efficient at doing this, but obviously you want to be able to do some of them that you can do by hand, because you can't do them all by hand for sure. But something like log base 3 of 81, so you have to remember, this is some exponent. Whenever you see log with numbers, it's an exponent. And that number is 3 to what power is 81. So how many times do I have to multiply 3 to itself to get 81? And that would simply be 4. Because 3 times 3 is 9, times another 3 is 27, times another 3 is 81. Next one, same idea, log base 5 of 1 6/25. So we have a fraction. So that's 5 to what power is 1 6/25. So now one thing is, if you take a 5 and then it becomes a fraction, then the only way to do that is with our negative exponent. So I know it has to be a negative value, because to go from a fraction to an integer or an integer to a fraction, we have to flip it over. So it's got to be negative. And then I just have to figure out how many 5s do I need to multiply to get 625, and it would be 4. Because 5 times 5 is 25, times 5 is 125, times another 5 is 625. Now this next one says log of 10,000 with no base. If there's no base, if you recall, this is called a common log, and it's just 10. So this is just asking 10 to what power is 10,000. And for tens, it's really simple because you're just trying to figure out how many zeros do I have, and I have 4. So a lot of answers of 4. Finally, log base 1/3 of 81. So we have 1/3 to what power is 81. So obviously we're going from a fraction to a non-fraction, so it has to be negative. And we already know it takes 3 or 4 3s to get 81, so negative 4. So those are several different logs with answers of 4 and negative 4, but very different answers, different bases, different values, but the exponent, all either 4 or negative 4. But again, remember, it's just the exponent that we raise the base to get the value. That's all a logarithm is. Now you'll find that at a lot of times we'll not only have to find log values, but we can actually use them to solve equations. So you can actually use this idea of rearranging equations to actually solve some of these kind of exponential and log functions. So if you look at this one, we actually have an equation with one variable x, that's here. This one we have one variable x, which is in the exponent, and this has one variable x, which is inside the log. So if we use this idea of rearranging from exponential form, which is y equals b equals x, to x equals log base b of y, we can switch back and forth to sometimes get the variable to an easier place to solve. Because right now my variable's in my base. Well, that's kind of impossible to deal with. In this case, it's kind of up here in my exponent, which we have done those before, but only if the bases match, and 3 and 7 definitely don't match. And this x is stuck inside the log, so it's kind of not in a great place. But if I rearrange this log function, so it's the base to some exponent equals the value. So again, it's just the exponent. The exponent was by itself. It becomes the exponent here. The base was the base. And then the value goes by itself. And this is something you could obviously solve because you could just take the square root. So x is equal to 9. Can't have negative bases, so we'll just say 9. Now this one's in exponential form, 3 to the x equals 7. So if I rearrange it going from exponential to log, the exponent goes by itself. It's log base 3 of 7. So again, I'm just using that rearrangement to solve it. Now the final one, we have log x plus 1 equals 2. No base, but we could put a base of 10 there. So if I rearrange it, we'll get 10 to the second power base, because remember, if it's the log, it's the exponents by itself, equals x plus 1. So that's pretty easy to solve. That's 100. I mean, the other one was not so hard, but this one's pretty easy. So x is 99. We'll practice some more of these here in a bit too. So this idea of switching back and forth can be super, super valuable for us. Now, when you talk about logs, there are several types of logs with lots of different bases. There's a couple that we kind of use quite often where we don't write the base. If you ever see the word log with no base underneath it, we're going to go ahead and assume that's base 10. And if you ever see the letters ln, ln is a log with a base of e. Now, e is just some weird number. It's just this weird transcendental number. It's kind of like a number like pi. 2.71828, something weird, non-repeating decimal, that we use a lot in science and different banking applications, a lot of different places, and we'll see E several places. But it's just this magic number that you see in a lot of formulas. So the log that has this base of E is called the natural log. So natural logs, a lot of times you probably can't do without a calculator, but common logs you can. So for example, this one says log of 1 10,000th. So remember, this is base 10, and so logs say 10 to what power is 1 over 10,000. Well, I know that it's negative because you go from an integer base of 10 to a fraction, and I have to figure out how many 10s do I multiply together to get 10,000, and that would be 4. 10 times 10 times 10 times 10 is 1,000, so 10 to the negative 4 would be 1 10,000th. Now these last two are natural log problems. This one you can actually do. It's a base of e, but it's basically saying e to what power is e to the 7th. So if I want e to some power to be e to the 7th, well, that's just 7. So that works out pretty nice. Now the last one is ln of 8. That's going to be tough because that's e to what power is 8. That's not really a nice one. It's just some weird number. So if I just type ln of 8 in the calculator, I'm getting 2.079. 3 decimals is typically sufficient. So it is some weird number. So e to the 2.079 is approximately 8. So they don't always work out very nice, but common logs more than natural logs. So that's kind of an idea of what a log is. So we're going to start talking about how we graph logs and then how we can use logs to solve some basic equations. So we've already talked about the domain of a logarithmic questions, if you recall from earlier in the course. We said the domain of a log are only things that are positive, because it's basically when you raise a base to any power, the only thing you can get is a number that is positive. So log domains are always strictly greater than 0. So if I'm looking for the domain of log base 2 of x plus 3, all I will look at is the stuff inside the log, just like before. When is x plus 3 greater than 0? Subtract 3. x is greater than negative 3. So my domain is simply from negative 3 to infinity. So again, stuff we've been doing all year. The second one, we have common log. It's log base 10 because there's no base given. Look at the stuff inside, and we'll solve that. So 4 minus 2x greater than 0. Now this one's got a little trick to it because we'll subtract 4. That's fine. Negative 2x greater than negative 4. But then we're going to divide by negative 2. Now when you divide by a negative number, remember, you flip the inequality sign. So now it's x's that are less than 2. So at all numbers that are less than 2, that's negative infinity to 2. Never bracket because you're never going to include that endpoint. Always exclude the endpoint. So now let's go ahead and look at the graph of a log function. All right, so let's look at the graph of this log. This is log base 3 of x plus 1. So if you recall, an exponential function looked kind of like this. So the log function kind of is reversed. Instead of having a horizontal asymptote, it has a vertical asymptote. And it certainly has a restricted domain, as we've already seen. And it has an infinite range, everything which is the reverse of our exponential function. So if we look at this, the domain, well, this is negative 1, so it's going to kind of start here. So if we do our x plus 1 greater than 0, the stuff inside the log, we know the domain is x greater than negative 1. We've already done that. Now, interestingly enough, this thing goes down forever and it goes up forever. Now, it goes down really quickly and it goes up very, very slowly. So my range is negative infinity to positive infinity. So this is the exact opposite of the exponential. We're switching the domain and range from the exponential because they're inverses. So we're switching their x and y values. Now, interestingly enough, the vertical asymptote, you can kind of see the vertical asymptote here as x equal negative 1. But ironically, it's always this number. Whatever the number is in the domain, that's also always the vertical asymptote. And it always kind of looks like this, right? Now, you kind of know your vertical asymptote. You know the generic shape of it. So we're just going to try to get some points on the graph. Here are some kind of nice points. The question is, how do you get those nice points? Once you get them, you can use transformations, shifting left, right, up, and down to get your new graph. Very similar to what we did with the exponentials. So every log has some key points, so this is pretty important. So if you're given y equals log base b of x, then the following points are always on your graph. Then the points b1, 1, 0, and 1 over b negative 1 are on its graph. Every time. So, for example, if we look at the problem above, it was log base 3. That was kind of the starting point, right? So if I started with log base 3 of x, I know the points 3, 1, 1, 0, and 1/3 negative 1 are on my graph. And then you can take those points, you can shift them left, you can shift them right, you can shift them up, you can compress them, you can reflect them, you can do anything you want to get new points for your log graph. So let's go and look how we do one of these graphs. So I have graphed the function log base 2 of x minus 2. Use transformation to help with this and check with a graphing calculator. So if I want to first look at the domain, so I look inside, I would start with there. So I want x minus 2 to be greater than 0. So add 2, x is greater than 2. So I know my domain is 2 to infinity. That's fine. But that also tells me the vertical asymptote is x equal 2. So I know there's going to be a vertical asymptote here. Now, as far as some points, what I would do is, what is the base of this log? I'm going to start with a parent function of log base 2 of x. Now, why that's going to help me If I think of log base 2 of x, then I know the points 2, 1, 1, 0, and 1/2, -1 are on my graph. Now looking at my function, the only transformation I see is inside I see subtracted 2. So inside subtracted 2 means I'm going to shift it to the right by 2 units. So all I'm going to do to find my new points is I'm going to add 2 to all the x's. The y's just stay the same. Now, could I add a y rule? Could I have a 2 out here and multiply by 2? Can I add a 3 at the end? I certainly could have, but in this case, the y's don't change. So if I add 2 to all the x's, I'll get 4, 1, 5, 0, and it would be, not 5, 0, that's not right. It would be plus 2, so it's 3, 1, and then 2.5 or 2.5, -1. So if I plot those points, there's 4, 1, there is, this is 0. I'm just not doing this right. So 3, 0, because the y's don't change, and then 2.5 and -1. So it looks like this. So I know my graph is going to get close to that asymptote, and it's going to grow and follow that general pattern. So you get these 3 key points, you have your asymptote, and then you can just use your transformations. All right, so the last kind of thing we're going to do is we're just going to practice solving some of these exponential and log equations. This is something we'll come back to in section 5 as well, to do some, quite frankly, more complicated equations. These are pretty straightforward. So we can use our idea of switching between exponential and log equations to solve equations. So if you recall, we said if y equals b to the x, that is equivalent, and it works both ways, of x equal log base b of y. So if you have something in a log form, you can certainly change it to exponential, and if it's an exponential, you can change it to log. Maybe it helps, maybe it doesn't. So these are in log, so if I want to change these to exponential, remember, the log of the base is 5, and remember, if it's log, whatever's by itself is always the exponent, so it's 5 squared equals x minus 1. So turning this log equation to an exponential equation makes it very, very simple. So this is 25 equal x minus 1, and then I'll just add 1. So x is 26. The next one's very similar. It's a log equation. It's almost set up the exact same way. So we have log base 8 of n plus 1 to the third. So this is 8 to the third equals n plus 1 when you change it. And again, very simple. 8 to the third is 512 equals n plus 1. And I'll subtract 1. So n is 511. So the last one on this one is kind of a little different. The actual variable, what we don't know, is in the base versus in the argument or anywhere else. So if I look at this, we take the base to the exponent. Again, with log, the exponent's always over here, equals 625. So not quite as easy a problem to do, but I can just take the fourth root of both sides. So b is 5, because 5 times 5 times 5, 4 times, is 625. So here we have some exponential equations. So sometimes switching these to log would be the easier way. So to do this, we have to get it to be something in an exponential or a log form. So I would go ahead and have to add 2 here. The key is you have to have the base to a power equals some number. And then I can change it. So remember, if I switch it, if I want the exponent by itself, then it's a log of whatever the base is of the argument. So the solution to this is just log base 7 of 10. Now this is not a nice number, this is some decimal. You could of course just toss this in a calculator and get the decimal approximation. But in general, this would be the exact answer. So the last one down here, very similar kind of thing. Now, a lot going on in this one. So first thing, I have to kind of get the base and the power by itself. So you might have to do a little algebra. So I can do 2 times 8 plus x plus 2 equal 10. I don't love that 2 either, but I can get rid of that by dividing. So I get 8 to the x plus 2 equals 5. So if you can get it to the base to a power equals 5, then we can do our switching forms. So the exponent, which is x plus 2 in this case, goes by itself, and then it becomes log base 8 of 5. Now, we still have the plus 2. That's fine. You can just subtract it. So x is just log base 8 of 5 minus 2. So, like I said, we'll practice a lot more of these when we get to section 5, but this switching form, pretty efficient. Now, it doesn't always work. There are problems where switching forms is not the only thing you have to do, but a lot of the times when you have log or exponential equations, switching forms can really help you solve the problem.